Hello and welcome. My name is Mr. Stabner and this is another lesson in logarithms. In the first video, we discussed the graphs of exponential and logarithmic functions and how they have an inverse relationship with each other. In this video, we will discuss various logarithmic properties that will allow us to rewrite expressions, which will be very beneficial to us later on when we talk about solving equations involving logarithms. Okay, let's begin. Due to the inverse relationship between exponential and logarithmic functions, they both can be rewritten as their inverse counterparts. We call this a conversion. So let's examine these two forms. Exponential form and logarithmic form, they both share the same three parts. And because of this, any sort of base, power, answer combination can be rewritten in both forms. In fact, sometimes the base that you're working with will change the type of logarithm you're even talking about. So let's take a look at this first example. 7 squared, 7 raised to the second power, equals 49. But that also means a log of base 7 at 49 equals 2. In this second example, we have 10 raised to the negative first power, which a negative exponent creates a reciprocal. So 10 to the first power just stays 10, but 10 to the negative first power becomes 1/10, which gives us this logarithm. Now, hopefully you notice, and it's not a typo, that there is no base written on this logarithm. That's because this logarithm is a special common logarithm. It is used so often that the base 10 is not written. It's similar to a 1 in front of 1x or plus 0. You just don't write it. So log base 10 is just the common log, or just log. But the power and the answer from our exponential form is now switched in their proper places. But common logs are not the only specialty type of log that we're going to deal with. We're also going to deal with what are called natural logs. Now, natural logs are called natural logs because of their base e. E is the natural number. The natural number that is just found everywhere. Similar to pi, it's found in nature, it's found in art, it's found in industry. It's all over the place when we talk about real-world applications. But e is just another base. E, this guy right here, is just another base. But e belongs to natural log, which we abbreviate to ln. ln belongs with e. E belongs with ln. Otherwise, it's just another base and log pair. So in this final example, notice that e is raised to the 0 power, and anything raised to the 0 power is going to equal 1. So what that creates is a natural log of 1 giving us 0. So let's practice a few more of these together. What I've built is a table that has some exponential form and some logarithmic form set up, and together we are going to turn these into their other form. Now if you want a challenge, pause the video, try these on your own, and then see if you have the same answers as I do. So let's take a look at the first one. The first one has a base of 3, so it's log base 3, but the 9 goes inside, the 2 now goes outside. So 3 to the second exponent equaling 9 becomes log base 3 of 9 equals 2. On the second row, we start with log base 7 of 1 over 343, and that equals -3. In exponential form, that's 7 to the -3rd power, which equals 1 over 343. On our third row, we have 10 to the 4th power equals 10,000. Now this 10,000 with its 4 zeros has that exponent of 4. When we turn this into a log, that base 10 is actually a common log, so we do not need to write a number as a base. We just need to put the 10,000 on the inside in its 4 zeros and equal it to 4. So when I want to rewrite the fourth one, noticing that it does not have a base on it tells me that its base is 10, and the power that our logarithm is working with is 0, and we already know anything to the 0 power is 1. Finally, our natural log pairs. E to the 2nd power is approximately 7.389, but decimals aside, the process is the same. E belongs to the natural log. So if I want to convert to logs, E belongs to ln. The natural log of this decimal, 7.389, is going to approximately equal 2. And finally, if I have the natural log with E inside, that's going to equal 1. If I were to write that in exponential form, you would see why. Because E is the base of the natural log, 1 is the power, and we already know anything to the power of 1 is itself. So E to the 1st power is E. So in this other part, we're going to be rewriting log expressions using properties. There are 4 main properties: the product property, the quotient property, the power property, and the change of base property. Now feel free to pause this video, jot these down. We're going to use them on the next slide to show how these properties work. But basically, how it is in the product property, you can rewrite multiplication inside a log as 2 separate logs being added together. Division inside of a log is actually subtracting 2 logs. If there is an exponent, a power, on top of a logarithm, that power can actually be brought to the front of the log and written as a coefficient. And finally, sometimes we need to rewrite a single log as common logs, and what we can do is we can rewrite it using this change of base, where the common logs split up the answer portion and the base separately, where the base lives on the bottom and the answer portion lives on top. So let's begin with the first 2. We have multiplication and addition. Multiplication inside becomes addition outside. This first one transforms into log base 2 of 3 plus log base 2 of x. Now our second one is separated, and if we want to condense it into one logarithm, the bases don't change, so it's still the same natural log, but this time x and y multiply with each other. But notice that they have numbers in front of the logarithms. That's where our power property is going to come in. The 1/2 is going to move up and become an exponent on x, but the 1/2 power really is the square root symbol in disguise. So really, for this second example, this is what's inside: the square root of x times y cubed. Now in the second two examples, division works with subtraction. This common log is going to start with a 2, but then there will be a subtraction symbol, and then the second common log will get written with an x plus 1 after it. Now be careful. This x plus 1 does not do anything else. Addition inside of logs is not one of our properties. Addition outside between two separate logs is one of our properties. Be careful, that's a common mistake. On our fourth example, subtraction between two logs becomes a fraction, becomes division. So we have log base 5 with x and y in division form. But notice they both have the 2 exponent, so we can actually put them together as one exponent on both of them. For the last two, I'm going to treat them more like change of base problems. I'm going to rewrite log base 3 of the square root of x in terms of two common logarithms. So since I'm doing that, I'm going to start by drawing a little fraction bar. And I'm going to put my base log on the bottom. Log 3, common log of 3. On top, I'm going to put the common log of the square root of x, but that square root becomes a 1/2 exponent in front, so it looks like this. 1/2 log of x. So now that last example is a little bit easier to see how it could transform back into the original single log. It has a log base 3 on the bottom, so it is a log of base 3. There's going to be an x on the inside, but the 5 in front tells me that it has an exponent of 5. Be careful with these properties. Multiplication is what creates addition between two logarithms. If you see subtraction, the number on the left is what goes on top when you put the division together. And if you ever have a number in front, it belongs to everything inside. So if there's two things inside, when you put the exponent on them, it goes to both of them or more. And finally, when you ever using change of base, the base bottom always on the denominator. Always. So thank you for watching. I hope you found this video to be informative. I hope that you have a better understanding of exponential form, logarithmic form, and the properties that intertwine together. Have a nice day.